Yeah, thank you everybody. So I will talk about the parcellation of the brain and the connectome. So what is the connectome? So the connectome is the network of the connections in the brain. We have different levels of the structural connectome. Just to mention this, while we have the microstructural connectome on the cellular level, like here nicely presented by Jeff Lifton, where we see like the single cells. But we also have like the more microscopic connectome, the axonal projection. So this is the side I want to speak about, but we have to keep in mind that there is a different definition of the connectome around, which is based on the functional network, which is based on the dynamic patterns of the activity of the brain, and which is a statistical independence of the coherence of the activity, and which is like very dominant in the whole connectomics literature. And some of the issues I mentioned here with the parcellation and the measure of connectivity also applies to this functional network, so maybe you can also apply something of what you learn here. But well, what is the basic components of a connectome? First, we have to do the parcellation. So first we have to have the nodes. Between those, we want to compute the connectivity. So these are a parcellation, which could be done like based on the surfaces, like here on free surfer, or based on cytoarchitectonics, or other issues. I will come back later to this. And then, of course, the edges, which are the connections between this. And in our case, it will be the extrinsic connections of done by diffusion tractography. One of the first, well, very dominant application of this connectome was done by Patrick Hagman, who proposed this like a long time ago, and who did this approach by segmenting the brain, getting the different regions, gray matter, white matter, do a parcellation of the brain based on the gyrification, and then very importantly, and this is often forgotten, he did a subdivision into very small areas along each gyrus. So each gyrus is jumped down in smaller areas with the idea to have homogeneous regions to compute the connectivity from. I'll come back to this later. And actually he used different subdivisions of this gyrifications. Here he cut it like just in 130, then in 240, 400 or 900 small parcels, and computed this connectivity matrix. And he saw that, well, first, some of the connections he got are just similar for smaller parcels or bigger parcels. This means that the rest of this parcel probably is just not involved in this connection. So having a huge parcel is not really a good idea to compute really the connectivity between those two, since only a small part of this parcel is involved in this connection. And the second thing he found out is the smaller the parcels get, so the smaller you do the subdivision, the higher you get the individual variability. So here you have the correlation between the different subjects gets down, which of course is maybe not what you want, but it might highlight like a higher sensitivity to variability between the subjects, or it might just introduce some noise. So there's some issues to be solved, like which is the best parcellation here. And so therefore I want to question this point, like what is the best parcellation. First, coming back to the classical subdivision, which was often used, like the Brodmann type parcellation. We have to keep in mind that Brodmann was based on cell distributions and not on connectivity. So the different areas have just different layers. The same is for the myeloarchitectonics, so they have locally different structures. This is not at all related to differences in connectivity. Using this parcellation to infer connectivity might be a completely wrong approach. The same is true if we use like the gyrifications. So we know that within a gyrus, like here in the motor stripe, we have the motor homunculus, so we have completely different functions along this central, along the precentral gyrus, and so also different connectivity. And the same is true for all the other gyruses. All these long gyruses, they have a completely different connectivity pattern between the anterior and the posterior part. So taking this as a region for connectivity analysis is a bad idea. the same holds also for functional connectivity. So this is just like, keep this in mind if you do it, if you have reasons, but keep this in mind that it's not a good idea. But, well, last year we had a good news that there was a new parcellation defined by Matt Glarso, who just presented this also next door here this morning. And is it solved now? Is this the ultimate connectivity pattern? So while we see that the large gyri are subdivided now, so we have smaller regions, so this is a good idea. But on the other hand, it's based on milo-array tectonics, so close to this, and on resting states. So is it the best for defining a structural connectivity matrix based on extrinsic connectivity, in particular since we know there's a huge difference between the structural connectivity and the functional connectivity. There is some commonality, but there's also a huge difference. So let's question this and look how we can do functional structural connectivity based parcellation, use the long-range connectivity to do both, defining the nodes and the edges of the connectome. So the idea is based on that different areas in the brain, like here, different areas here in F1 in a monkey, have differences in the connectivity profile. So this area has a different connectivity profile than the other one. So we can use this connectivity profile to define functional areas. So we do like the seed-based connectivity analysis. So we seed at the gray matter, white matter boundary, as also Maxime suggested this morning, compute different probabilistic tractograms like here, and then compute just the similarity on the whole brain level for the different connectivities. So we don't look only at the endpoints, to compute the connectivity and to compute the similarity between the tractograms, but for the whole white matter. The main reason is that, as we saw before, like if we do probabilistic tractography, we have high values in the white matter, and the closer we come to the cortex, the lower gets the intensity, and the higher gets the noise level, like the estimation bias. So if we take only the endpoints, we'll have a lot of noise in our connectivity estimates. So this is something which is also have to be kept in mind. Also, if we use this tractography and streamline counts for the measure of the connectivity, and if we take only the endpoints, we are very sensitive to the most noisy part of the tractogram. So take the whole brain, compute the similarity, very simple, get the similarity matrix, and do a simple clustering, and then you get the parcellation out of it. So this can be done for like different areas, like here for the infrafrontal gyrus, which have each representative different connectivity profiles. Can we do it also for bigger regions? Well, then we cannot build up in a single matrix the whole thing, but we have to do it in a hierarchical way. So how can this be done? So we start with single seed points in the brain, join together points which are the most similar, compute again the similarity between these points, group them together to build a whole hierarchical tree. So this is the whole brain, and it splits down to different leaves. If we do this then for a small region, like for example here for the infrafrontal gyrus, we can cut it at a certain level. We get like 2 areas. We cut it a little lower level. We get here 4 areas or even more, and get such a hierarchical representation, a hierarchical connectome, well, a hierarchical parcellation which can be used for a hierarchical connectome. Very nice idea, but the problem was that, well, we can do it at different levels, but which one is the best cut level? Well, probably we have to use several levels and do the analysis again on several levels. The next point is like how to do this. Well, we had here a software which was implemented in an interactive tool which helps you to explore like a little this structure, which can be downloaded here in this GitHub repository. And if you want to see the developer, David Moreno, he's also here at the conference. What is very nice is what this idea was taken up by the group from Rashid Derish and David Wasserman from Gallardo, who published a paper on this, how to do this in a group-wise level. So he does this on a single subject level and gets this similarity matrices then on a group population average to do a group-wise population based parcellation. There's also a new poster tomorrow where he extended this approach. So this is a way like to get a group-wise parcellation based on the tractography data, and which could be used for the connectivity analysis. But one important questions we always have to keep in mind, like if we do this parcellation, how sharp are these boundaries? Can we really speak about parcellation in this context? And this was first pointed out by Leonardo Ciarellani and later also by Claude Bajada, that well, somehow the connectivity profile changes from one area to the other for certain areas, but for others it might be more a gradient. Well, this color still looks like in two categories, but actually it's more or less smooth gradient, which changes from one typical connectivity profile to another without showing a clear, sharp boundary, but it's just a gradient. So the connectivity profile here is different from this here, but it's not in two parcels, but it just changes across the brain. And this might be something which holds also for the whole brain, that the connectivity profile changes smoothly in certain dimensions. And this is quite a challenge also, like how can we integrate this in connectomic analysis? So the hierarchical approach might be one way, but maybe we have even more intelligent ways to integrate the smooth changing connectivity profiles. So looking forward what this will give us in future. But let's go back to the simple approach and just subdivide the brain in different areas and define the connectivity. Well, how can we quantify connectivity? We saw before that we shouldn't do streamline counting, but what is done and how do we get to nature neuroscience? We do streamline counting. Well, we do the correlation between the number of streamlines and some behavioral trait, and we got these nice correlations. And well, is it random? Well, let's have a closer look on the streamline count and how can we trust it. So, well, how it's this generally done? Well, we saw before, like we define some regions, then we compute like the relative number of streamlines seen in some regions, which go through another area, and compute just some connectivity index. But well, of course, we have to take care, since if we do like seeding, for example, here in this axial slice in the inferior lobe, when we just get like streamlines, probabilistic streamlines coming here to the front, we'll see that some end here, some end here. And if we want to take the connectivity to these two target regions, we have to take in mind that some of the streamlines might just cross several of these target regions. So it crosses here the black line and then the other one. So do you count the streamline twice or not? Very difficult question. The next point is that the endpoints, as you see it here as an example, are concentrated on the crown of the gyrus. So if you want to get fibers ending here, as Maxime pointed out, you have to have a special tractogram algorithm, which isn't available yet. So we will get this gyral bias, which I will mention later, and this will influence also your connectivity count, in particular if you have regions which are like placed more on the top or more in the bottom of the gyrus. And then of course, like we have this distance bias, the farther away we are from the seed area, the lower is the connectivity, just exemplified here by a lot of streamlines ending just here and very few here, which might be true, but which might be also just an artifact of the method. Coming back to this gyral bias, this was published like I think 2 years ago, 2015. And it was the simple observation that most of the streamlines just end up at the gyral crown instead of ending here in the sulcus, since like the streamlines just pass by, since the local orientations are just tangential to the gyrus in the wall here, in the sulcal wall, and also in the fundus, and they are just perpendicular to in the top, and this leads to a main ending bias in the crowns of the gyrus, which is probably biological not plausible, and which can be solved maybe with new algorithms, as Maxime pointed out. The next thing is the EPI distortions. I agree that seeding at the gray matter white matter boundary is very nice, is the best way, but you must take care that the registration is done properly. So Alexander Lehmans proposed like to register the diffusion images on the anatomy images. Another approach was proposed in the context of the Human Connectome project by the FSL group was the algorithm which they call top-up, which uses two different phase encoding images to correct for this EPI distortions. Another algorithm which was proposed by and implemented in the SBM toolbox and proposed here in this toolbox by Siavosh Mohammadi and Lars Rutotto was the HISCO, so a hyperelastic registration algorithm, which uses also these two phase encoding directions and computes like a mass preserving solution between both images. Of course, you can also apply field maps, and in this small comparison, like these two algorithms which uses the histoelastic registration, just performed as good as one each other, and did a quite nice correction. But still it's not 100% safe. So take care if you do it, and you might also do some errors doing this correction, so it's not so simple. And well, if you do all this and then we compute like the connectivity between the different regions, like look how the connectivity looks like. So we compute like from one of the seed regions, connectivity profile on the surface, and then we quantify it on some target areas and just look on the connectivity values. Well, we see here like the red area has here a stronger connectivity like the yellow and the green areas. So this is very nice. So we can use it for the parcellation, and they differ in the connectivity. But what I wanted to point out here is this strong variability across participants. So here we have like an order between like one connection and more than 1,000 across subjects. So this is here a logarithmic scale. So we go over several orders of magnitude from 10 streamlines to 10,000. So this is not variability which would be in any way biological plausible and explain some variability between the subjects, but this is really an unexplained variance which questions again this correlation with behavior if you do it in a linear way. We didn't want to believe this and try to do our best. We did 7 Tesla diffusion MRI at 1 millimeter isotropic resolution, and well, again, bedpost X connectivity, and seeded here for some areas in the prefrontal area and computed the connectivity to the thalamus. Well, we find again, like in this logarithmic scale, like a nice stable connectivity profile, a little lower here. But if you remove the logarithmic scale, then you see that this one has just like nearly no connections compared to the other one, which is on 100,000. And it's again like a huge variability across subjects. So don't trust this connectivity values for comparison between subjects. So what can we do? How can we do it better? Is it because of the tractography algorithm? So we tested out, and there are other papers who did the same thing, like different probabilistic, deterministic tractography algorithms with different local models, and compared everything on this certain areas, computed this connectivity matrices, and got this connectomes, like this connectograms for the different areas, and you immediately see that they differ really strongly between the different methods. So not only the within subjects it differs a lot, but also for the different methods it differs a lot. So there is no good solution in this way. So what can we do if we cannot go in this way? We can do a different way to quantify connectivity. So one way, which was also mentioned before already, and which will be picked up later also by Yeatman, is to use like quantitative measures along the tract. So we can use we can use something like myelinization, since we know that the information transfer, like the amount of information or the amount of the influence an activity in one region can have on a second region, and how much time it will take depends on the myelinization and the axonal diameter of this connection, and also of the fiber density of this connection, and of course the length of this connection. So we should have, instead of counting streamlines, have estimations of this 4 parameters: diameter, myelinization, and density of the fibers, and use this as measure for the connectivity to put this in a somehow enriched connectome. So how can we do this? Well, one approach was here that you measure quantitative T1 and T2 maps. So you measure the quantitative relaxation time in every voxel and map this along the track. And the T1 relaxation time should be linearly related to the myelinization. There are other approaches like the macromolecular volume fractions, which we will hear later. And once we have this mapping along on the track, we can do like a sort of integration along the track to get like the possible information transfer time or amount of information which can be transferred along this edge. Axonal diameter. Well, we heard before that probably it's not so robust to estimate the axonal diameter exactly for the different fiber bundles across the brain, but maybe we can at least differentiate if this axon has large fibers or smaller fibers. And this was proposed here by Shani Ben Mati from the group of Yanef Asaf last year at this conference. So they measure like different diffusion times, as we saw this morning for this Excalibur, but they don't do it only for one direction, but for a lot of directions. So we do a full shell of 7 different p-values, a total of 96 directions, with each measured with 3 different diffusion times to give access to the fast and slow diffusion compartments, so the intracellular and extracellular diffusion compartments. And we can get like a fitting of 2 distributions, so we know there are smaller axons and bigger axons, so we don't fit exactly the diameter for these axons, but we just check how good is the fitting for distribution of smaller axons and how good is the fitting for larger axons. And we get here this ratio between small and large axons, and we see here smaller axons in the lateral side and a larger axon here in the cortical spinal tract. So we repeated the same experiment here on our new Connectome scanner, like the one which was installed some 5 years ago in Boston. There were 2 new systems installed last year in Europe, one in Cardiff and one in Leipzig. And this stronger gradients, as we saw this morning in the talks, allows to give us shorter diffusion time and to give access to this also the smaller axonal diameters. And if we measure this, we can see here for the whole brain, this is like the proportion of large fibers in the brain. We see here, for example, like the fibers in the corpus callosum connecting the motor areas have larger axonal diameters as, for example, other fibers here. So the corpus callosum and the cortical spinal tract show these large fibers. And here the distribution of smaller fibers. So this is the density of small fibers in every voxel shows up like a lot of small fibers in something like the SLF, the arcuate fascicle, compared to like the cortical spinal tracts, which have more this large fibers. And here an example phenomena that they have like a lot of large fibers and a lot of small fibers in the area connecting the 2 visual cortices. So this means that we have a large spread of different connectivities, so large fibers, a lot of large fibers and a lot of small fibers, compared to, for example, here the anterior part of the corpus callosum, where we have a lot of small fibers. So maybe this connectome might give us an approach to get a better estimation of the axonal diameter, together with T1 relaxometry, we can maybe get a better estimate of really the quantitative connectivity between the different areas. And I just wanted to mention that those scanners are now not, well, there are only 3 scanners available in the world, but this shouldn't limit the research only to these 3 sites, since, well, at least the Leipzig one is open, so everyone can come and run projects on this, and this even relatively easy, so without any charge available. So please, if you are interested, come and join us. So, well, to summarize, we saw that diffusion MRI can be used to study like the connectome in a structural sense, and be used also for the parcellation and the connectivity analysis. And to put this in a network-based analysis, which I didn't put on, like there was another session parallel here that we did this network analysis once we have the connectome. Of course, you can all do this network statistics on this. And how to integrate this with the cognition is still very challenging, and I wouldn't dare to go too far there. So thank you, everybody. And if you want to see more of this, there is some literature on this very classical diffusion MRI. Thank you.